22 million years ago, there was a collision in the asteroid belt. That collision, incredibly, has produced some meteorites that only recently, actually back in 2015, landed in Turkey. Incredibly, this is evidence of a cataclysmic event 22 million years ago. And we've now, because of research team that our own Peter Jenniskens has been part of, have determined that these meteorite fragments found in Turkey just again recently have been now discovered to be remnants from that incredible collision. So an amazing, I guess an amazing event of scientific sleuthing. It's long been thought that some meteorites and meteor showers are leftover vestiges of this great collision, but now we've got some definitive proof. So today we're going to meet Peter. Some of you have met him before in other SETI talks here at the Institute for Facebook Live, but we're going to talk to him again about this program, about this event, and we issued a press release actually a couple of days ago on the 18th of March about this research. It's a large research team of about 75 scientists, so there's a picture on the front of that press release of the asteroid Vesta. All right, so my name's Bill Diamond. I'm the CEO here at the SETI Institute in Mountain View, California. Let's go talk to Peter and find out about this 22 million year old detective story. Peter, how you doing?
Good.
All right, good to see you.
Good to see you.
Lovely shot in the back. I like that picture. And yeah, so
Courtesy of NASA Ames.
courtesy of NASA Ames, a beautiful picture from our friends down the street. Well, anyway, I've just kind of described this as like a 22 million year old detective story.
Yes.
So it's really fascinating that we've been able, after all this time, to kind of definitively determine that these fragments are from, as a result or byproduct of that collision. How was that?
Well,
How did that happen?
The definitive part is the part that will undoubtedly be discussed. But,
Sure.
But it's definitely...
The evidence is strong, let's say.
It's definitely a very interesting story. It has many little leads to the ultimately trying to solve the crime.
All right,
That
so
is,
like any good detective story.
where do our meteorites come from?
Yeah, right.
And, a lot of the meteorites we're getting on Earth are from the asteroid belt. Most of them actually are. We just don't know exactly where in the asteroid belt they're coming from.
Mm-hmm. And so we
one
don't know
time-
where or from which object.
Yeah, exactly.
I mean,
And
it's one thing even to determine where, but another, it seems, to determine that not only do we know the region where they came from, but the actual source.
Yes,
That's
yeah.
unbelievable.
That's the holy grail.
That's the
to
holy grail.
Point to the crater or the site where there was a big collision, and a lot of debris was created, and then after a long time it hit the Earth, and some of it fell on the ground, and we could collect it. There is one case that people have always been a little bit more certain about, and that has to do with the asteroid Vesta.
Okay.
Vesta is the second largest asteroid in the asteroid belt,
Right.
500 some kilometers. It's really dominant.
So this is, how far out is this from? So this is in
We're talking the area between Mars
and Jupiter.
There are a lot of asteroids there. Most of them are the product of collisions between asteroids that created these debris fields. And we have lots of debris fields there.
I mean, these are essentially leftover remnants from the formation of the solar system.
Exactly. There's a couple of asteroids that are still pretty much the size that they were when they were formed. And so Ceres is an example where the Dawn mission visited. Vesta was another case. And Vesta was hit badly a long time ago because on the southern hemisphere there's a big impact crater, a big impact basin, two of them actually, that cut a big chunk of the southern part of what normally would be a spherical thing. It cut a big chunk out, and it's called the Rhea Silvia impact basin. And what that did was it created a lot of smaller asteroids that are a big debris field that stretches from Vesta all the way to what we call the 3-to-1 resonance, which is an area in the asteroid belt from which we also get meteorites. It's where the asteroids move 3 times around the sun when Jupiter goes around once.
Okay.
So if you have that sort of a resonance in time that they go around the sun, then it's dynamically a dangerous area to be in, and it sort of marks a spot in dynamical space in the asteroid belt that's important to us.
Mm-hmm. So if we think of the asteroid belt as sort of a ring, is this on an outer or inner boundary, or is it a particular portion of this
It's
ring?
it marks the outer edge of the inner part of the asteroid belt.
Okay.
So you have the inner part of the asteroid belt is marked also by a resonance, but it's a secular resonance called mu6, and then the outer part is marked by this 3-to-1 resonance, and then you have the middle part, which is marked by the 5-to-2 resonance, and then you have the outer part of the asteroid belt. Most of our meteorites are coming from the inner part and from the middle part of the asteroid belt, we think. If they come from the outer part, typically what happens is an asteroid, you have a collision event, you have a lot of debris created, little pieces. Those then are exposed to sunlight.
Mm-hmm.
The sunlight heats the rock spins around, it radiates the light in a different direction, and so over time that changes the orbit period of the rock.
Mm-hmm.
And so it can get into a wider orbit, it can get into a shorter orbit. In both cases, at some point it's going to end up in one of these resonances.
Mm-hmm.
And when it does, then very quickly the orbit becomes, instead of circular, it becomes elongated. The nearest part to the sun comes in, the furthest part from the sun goes out. If the furthest part of the sun goes out and hits Jupiter's orbit, then Jupiter very quickly sends it away.
Yeah.
So that's why in the outer asteroid belt, things tend to be sent away before they can ever.
Now,
reach
when
the
you
Earth.
say sent away, they just go out into.
Yeah, they can get into an orbit that
really
that
elongated
throws it
orbit.
away, very elongated, or throws it away out of the
Yeah.
solar system.
So how do the orbits of these debris fields get to a point where they intersect the Earth's orbit?
It's mostly because they then get very eccentric, very elongated.
So it's that eccentricity.
And so this point that is nearest the sun comes in closer and closer and closer, and at some point it can actually intersect with Earth's orbit, and then we have a chance that something hits us.
Yeah.
And so
By the way, Peter
Yeah.
gets excited when things hit us, but not really big things, just little things.
small.
'Cause then he can find them. And we
We're
can
interested
learn
in the
something.
small things at this point, yeah.
Yeah.
So the story is twofold. You have this impact in the asteroid belt that creates a lot of small pieces. Then you have this process where very gradually the orbit changes, and you hit one of these resonances. So you basically have this debris field there. Then some of that debris hits the resonances, and then once it hits the resonances, then very quickly it gets into these eccentric orbits, and then comes close to the Earth. And then it can actually interact with the Earth, so it can come close to us. That can actually steepen up the orbit,
Mhm.
and at some point it's going to be fatal, and then this rock is going to hit the planet.
Mhm.
And that's sort of the sequence of events. And so when we find a meteorite on the ground, the question is what can we do to try and figure out where in
Where it came
asteroid
from.
belt this came from?
Yeah.
And this case, the Sarıcicek meteorite that fell in Turkey on September 2 in 2015,
Mhm.
turned out to be just a fascinating story, fascinating detective, because we basically started, where we found it, and then we sort of traced it in various steps all the way back to assigning a crater on Vesta.
And you were able to trace it back by virtue of knowing the trajectory of its
there's a
incoming.
lot of little pieces to
Mhm.
this story, and all of the pieces have, you can debate endlessly about it, how good it is and how valid it is, and so I'm sure that this story will develop over time and will
Sure.
become more certain. But in this case, we have a really cool lead, I think, and we hope that it will hold up in the future.
So now the research team is pretty large. There's what, 75
Yes,
scientists on this stuff?
79 people participated in this study.
But and they're from all over the world, different
Yes.
academic institutions,
Yes.
and very prestigious group of researchers.
Yes.
Is there pretty much consensus within that group in terms of
Everybody
evidence?
in the group contributed a little piece of that puzzle.
Yeah.
And they all with some nuance articulate what it is that they found, and then in the end you build up this picture where you put all these puzzle pieces together, and then you see how that turns out. So that's the cool thing about this paper, is that a lot of groups came together, focused on studies of the meteorite, focused on dynamical aspects of the evolution of rocks in space, There were, of course, the work that was done when Dawn mission visited Vesta,
Right.
and it mapped out all the craters on the planet.
When was that, by the way? When was the Dawn
2010 and
mission?
2011.
2010 and 11.
Yeah, it's
Okay.
been a couple of years.
Yeah.
SETI check, when it fell in 2015, was just a few years after that, and so we had all this information about Vesta, and suddenly here was a meteorite that turned out to be very similar in composition than the stuff we find at the surface of Vesta.
Mhm.
It's an eucrite-rich howardite.
Now,
Yeah.
before you go into that composition aspect, and you speak of meteorite, how many fragments was found? Was it only one piece, or were there lots of little fragments?
Yeah, the story of the fall is very cool.
Because you went to Turkey
I did,
back then to
I did.
join the team,
so,
right?
I brought with me the little note that our admin left on my desk and says, please call the gentleman from Turkey ASAP. He sent you email too, thanks.
So this is back in 2015?
That was back in 2015.
And that's the oldest post-it. I've never seen anybody save a post-it that long. That's pretty cool.
So this gentleman was Ozan Unzalan, and
Yes.
he's a young researcher at...
He's watching.
and
He's watching.
He's online.
All right,
This is
there he is.
Ozan.
All right, everybody give a shout out to Uzan and say hello.
Yeah.
That's very cool.
I had just
Nice to have him with
I had
us.
just met Ozan at a science conference. Probably a few months before that, and we had talked about, what it takes to recover a meteorite, but also to observe how the rock is coming to
Right.
the atmosphere. So
Right.
in order to get a trajectory and an orbit, an impact orbit. And Ozan was setting out to set up cameras in Turkey and to try and film the impact of these meteorites. And so a few months later, suddenly there was this massive impact, and it happened in an area around the city of Bingöl. And Bingöl is in the eastern part of Turkey. It's a very restless area, a lot of safety concerns, and so the local universities had a massive amount of video security cameras set up. And so all
because of all the
because of
security concerns.
Just security concerns.
that's
And
fine.
so all these cameras were just a bonanza for us, because a bunch of
They
them
captured the
saw this
No
saw this
kidding.
fireball.
Ah.
And so when Ozan told me that yes, there was a meteorite fall in Turkey, and very interesting fall, big one, and so on. I was very interested, but you really want to have the observations of the fire. You want to be able to get the track, and you want to have a piece recovered. So I asked him, well, see if you can get a piece and send it to us and see if it's something interesting we could track. And so when Ozan sent me a fragment, it very quickly turned out to have this shiny crust. It's very different than other meteorites.
Is that what you see in the picture there? Because it does. That first picture has a very
yes,
shiny.
exactly. This shiny
That's it.
crust to it. That's a hallmark of this type of meteorites. So the ones that come from Vesta.
And does that
And,
shininess have a result of the heating that happens when it goes through the Earth's
So this was
atmosphere?
one of the aspects studied in our paper. A group in Bulgaria did a lot of work on this, and a group in Russia, and they found that the reason it's shiny is because the crust is filled with little bubbles.
Ah.
So the crust, what you see, the covering of the rock, it's a melt crust. It's basically what happens when the rock goes to the atmosphere, gets hot, and also cools very quickly because all the melt is blown away.
Yeah.
You're left with this little thin layer called fusion crust.
Looks like almost like a glass layer.
Yeah, glass layer, and that's what it is. It's a glass, and that's how you recognize a meteorite. So if you look for meteorite, you don't find it by holding a magnet to it, or you find it by looking for this crust. It's a very thin layer.
So as a sidebar,
Yeah.
when we did the FDL project, where you developed using artificial intelligence
Yes.
and machine learning, so you developed this algorithm to recognize from drone a flyover a
Yes.
meteorite and distinguish a meteorite from a rock. Was that one of the
That was one of the
characteristic elements?
aspects we were looking for.
Interesting,
Exactly.
yeah.
If the rock is broken, then you can very clearly see that. It's a
Yeah.
very distinct. The inner side is a lighter color usually, and then the outer side has this really dark, thin layer on it. And
Yeah.
In this case, that layer, that glass, is just riddled with bubbles.
Yeah, yeah.
And that reflects and reflects the light, and that gives you this sort of sheen to it.
Now, what's
And
the
that
scale?
that made it actually very easy to find them.
Yeah,
because,
exactly.
it
Because then
took
they're very
us-
reflective, right?
It took us just a few minutes to go there, and I found myself one of these meteorites. So it was very exciting, just
So-
because of that.
How many fragments were found altogether?
So in the
this?
end, 343
Oh, a
fragments
lot.
were identified. Yeah.
And any, now, this was a pretty big fall, it appears. Did any fragments do any damage anywhere, or were any things,
No,
like falling through people's roofs, or?
No, and not in this case. The meteorites fell in the fields,
Yeah.
open fields, and there was no damage done as far as I know.
When they fragment as a result of the heating process of coming through the atmosphere as
Yes.
well, that breaks them apart, essentially.
Yes, and that's a actually very important process, because if you have a really big one like jelly beans,
Right.
it really depends on what altitude all this energy is being, the energy of motion, the fact that,
yeah.
that you have a, in case of jelly beans, a 20-meter rock coming in at 19 kilometers per second.
Yes, yeah.
All that motion, you have this big collision. Where does all that energy go? And that depends on how it breaks up.
Yeah.
And so one of the aspects that we were interested in this case was to investigate how the breakup happened.
Yeah.
So Ozan called me.
No,
sent
just
this-
let me,
yeah.
let's go back to this for a second.
Yeah.
This is worth noting. So Ozan, I want you to be very proud and impressed. So I don't know, I've been alive for I don't know how many 100 years. I've never had anybody call me that it was so important that the Post-it that told me about the call was saved. So this is pretty cool. This is a 3-year-old Post-it the day you called Peter.
Yeah.
So that's pretty cool. Anyway, all right, back to the
So that was
back to the call.
It was a great moment.
Yeah.
That started the project, and so a month after the fall, Ozan took us into the field
Mhm.
to the city of Bengal. And in Bengal, he had organized for incredible support from the police department.
Yep.
We were picked up at the airport by our host there. I vividly recall the first thing she did. Came fresh off the plane with Ozan, who joined me in Istanbul. We arrive on the ground. We are greeted by this very friendly person. Invites us to come and sit in the car. And the first thing she did was she grabbed into the glove compartment, took a handgun out, and put it between her legs. And in that way, she drove us back into town.
Nice.
So I'm thinking, okay.
What have I got myself into? Wow.
So I have a wonderful souvenir from the Bengal Police
I was
Department.
wondering what the hell
we
hotel
stayed there.
slippers
They gave us,
we're doing
They
here.
gave us a lovely place to stay, and that's where we spent the nights in that area. This is my
Who
proud
saves
souvenir.
this kind of stuff? I mean, that's just amazing. I thought you were going to say, well, we have these special slippers that
No,
we
no,
use
no,
in the
no.
meteorite
Yeah,
field. Okay, so that's your souvenir from
That's
the hotel.
my souvenir
That's
from
awesome.
where we stayed. And so they then took us to the university in Bengal.
Mm-hmm.
And the university in Bengal was also immediately excited about this project,
Yeah.
to have this rare of a meteorite come down near their town. And they immediately wanted to give us all the support we needed. So we visited the video security office. They had 200 video security cameras set up. A big bank of video screens, just to
Unbelievable.
scan through them.
Yeah.
And we spent some time just looking at all the videos and going through the time when this happened to see what we saw, and in the end settled on the 5 best videos
Mhm.
that we thought were good. They had most of them had just the shadows in them, because in Bengal was so close to the track itself that the meteor itself was high in the sky.
Uh-huh.
And so most of the cameras are looking down on terrain,
Down
and
low,
buildings and
yes,
so on.
yeah.
And so you see shadows. And
But from
one
that,
of-
you were able to derive trajectory.
Yes,
That's
and
incredible.
I bought another picture. This was sort of the story I just summarized on. But this is a picture of the rectorate building in Bengal, and the tip of the corner of the building there was seen as a shadow on the plaza here.
Huh.
And they brought in a fire truck to help us measure how high that exactly is.
Come on.
So here you
So
see
that's what's going
Ozan
on?
and you see me there up in the
You're up
middle.
in the fire. Oh, that's
Fire truck.
unbelievable. So first of all,
we
you've had.
determined exactly the height from the tip of that
That's
structure to the ground. So
insane.
we had our angles.
So this is why
Yeah.
people go into science.
Yes.
Because they get to climb on the top of a fire truck, they get to have an armed escort from the research field. I mean,
Yes.
it's pretty exciting.
It was fantastic.
That's
And
unbelievable.
So we got, with the shadows, we got the angles measured, and from that we could actually see the meteor move in the sky.
So these
how
are
fast it
shadows
is
caused by
moving.
the light from the
The
meteor.
light of the meteor.
Wow.
This was a nighttime.
So it's
nighttime
a glowing event. Wow.
And so we did that in Bingo. We then traveled, Ozan and I traveled to Moes Alperslaan,
Mm-hmm.
which is about 100 kilometers closer to the Iranian border. We, kept a low profile, so we're traveling in one of these little vans,
Mm-hmm.
and on the way back, the driver was on his cell phone. It was pouring rain, and he was making shortcuts on the highway.
Oh.
and Ozan was, we were sitting in the back of the van
White
with our
knuckle
nails in the seat.
Unbelievable.
And Ozan, he got upset, and he told the driver to, please pay attention and so on. And I later learned this because this was all in Turkish. But I later heard that the reply from the people in the van was, "Why do you worry? The drivers are always driving like this."
It's like, okay, standard procedure.
Exactly.
Unbelievable.
So in Moes Alperslaan too, we got incredible support. So we again found 102 or whatever video cameras.
I think it's fair to say we're glad
Yeah.
to have Peter back in one piece.
Yes, there
actually,
we
for
are.
this event, so.
And so we got some video from that, and from Moes Alperslaan and Bingo, and also from some other sites,
Mhm.
we were able to then triangulate the track, get the trajectory out, and determine how fast this thing is coming in, and at what altitude it broke apart.
Mhm.
And so then, once we had all that information, we're very keen to go to the area where the meteorite fell. This is the little town of Sarıcıcak. Sarıcıcak means yellow flower in
Okay.
Turkey, so it's a very appropriate name.
Yeah.
Lovely farming community, not too far from Bingo, on a little hill and surrounded by areas, by fields and so
Yeah,
on.
yeah.
And it was really, this is Ozan and I there in that area talking with people.
Oh, he's got his California athletics shirt on.
He got a funny athletic shirt.
So,
Uh,
by the way, so we know that Ozan is watching. If there's anybody else watching us from Turkey, let us know and we'll give you a shout out.
Cool.
Because and like
We
always,
do. We
let
have
us know.
somebody from, where is it? Istanbul.
Yeah.
And somebody from somewhere else.
Cool.
Begu from Istanbul.
Begu from Istanbul. All right, welcome. And very cool.
Very first thing was obvious that people were incredibly friendly.
Yeah.
I mean, again,
Helpful.
Helpful.
Yeah.
Again, the person who was really putting this from the local villager side was Nazir.
Gentleman in the middle?
Yeah,
Yeah.
person in the middle.
Mhm.
He really, understood that this was interesting, important.
Good.
He took us to the area where they had found a bunch of meteorites already,
Mhm.
and as I said, within minutes I found one.
Yeah.
And here we're looking at one of the finds at some of the locals.
Now, was that typical of the size of the fragment you're
Yes,
picking up? Sort of
yes.
like this tip of
Very
a thumb
small,
size?
very small pieces.
Yeah.
This rock really broke into tiny fragments.
Amazing.
And so Nisir Agun, he was really the person that really made a lot of the research possible that
Mhm.
we ultimately ended up with. So
Excellent.
they made some material available for our studies that we could go and study the rocks.
Mhm.
But more importantly, they gathered all the information from the town, and they started gathering where exactly different meteorites were being found.
Yeah.
And that in the end really mapped out the strewn field very nicely. So this was one of the meteorites.
Okay, can you go back to that? Because that's a
Yeah.
good scale shot.
Yeah, this shows one of the
1
rocks
centimeter.
being found.
Okay.
So this is a centimeter. So you
Yeah.
see that these are all small, very small rocks.
They also have sharp edges, it looks
Yes,
like.
yeah. So the way they, in the end, we were able to determine that the way they fragmented was that big chunks would break into smaller chunks, and then the smaller chunks would break into even smaller chunks. So there was this fragmentation going on.
So it wasn't a
Not
single
like
process,
that.
it was a...
It's
it
really
was,
a cascade.
Cascade, yeah. Interesting.
And that's reflected here because you can see this side was only very mildly. This may actually be the fresh surface, and this surface very mildly fusion crusted.
Okay.
So that
Yeah.
broke really late when it was coming down. It was still moving pretty fast
Mhm.
because
that
it was fusion crusted a little bit,
Yeah,
but
not as
then
much
it was
as other
slowed
parts.
down, and then that process stopped. Yeah.
Interesting.
So,
Okay.
so yeah, those are the things we're looking for when we find these. If you find a meteorite yourself, then the one thing you can do is you can try and collect it pristinely, so you can make sure
Yes.
that organic material
Doesn't get on
doesn't
it.
get on it.
Right.
People don't breathe on it. You don't touch it. You collect it with some aluminum foil.
So is
that
that what
stays fine.
you've got here is...
These are actually some of the pieces that were
Mhm.
originally made available for the study. So this
Yeah.
is actually the meteorite.
So would you pick them up like that with tweezers of some sort and be careful?
And then be
not to
careful
touch
with it.
Yeah.
I actually use aluminum foil in the field.
Mhm.
That works just fine.
All right.
So this
Can
is-
we bring the camera
yeah.
in close for this?
This is one of the meteorites that was studied in this rock, and you can see on this very nicely the fusion crust. So you see this very black material that is that makes it melt.
That's where it gets classified.
The glass, that's the shiny stuff, and then this is the inside.
Mhm.
You can see the inside is very diverse.
Can
here.
turn, so the
Yeah.
inside here, yeah, that's really interesting. So you go from a shiny, dark gray, smooth outer surface to a more
Yeah.
rocky, it looks more like a conventional
Yeah, so if you
rock.
find a rock like this on the ground, that gray rock, you wouldn't recognize it as a meteorite. I mean, it's not the
Right, that looks like a rock.
It's not the inside that makes a meteorite
Right.
look a meteorite. It's
But
really
that shiny
this
surface on
this
the
surface,
outside.
yeah, and the
Yeah.
fact that it's a fusion crust. So it's
Yeah.
really a covering. That's what gives it away. And in
Yeah.
this case, the shininess was also something that really stood out.
Yeah.
So you could see there were a lot of other rocks in the field here. There's a little black dark rock sitting here, for example.
Yeah.
But just the look of it was quite different. This is a lot
So you can
darker,
tell. Yeah.
and it had this shiny glow on it. I'll
Yeah.
put this again.
So folks, that's a visitor from outer space
Yes.
from a collision 22 million years ago.
Yes.
That's pretty cool.
Yeah.
Yeah.
So of course we didn't know that at that point. That was the information we later got out.
Sure.
But yeah. So this was the strewn field we got. This is a 2 kilometer bar. So you can see sort of the areas where these rocks fall are always spread out. It's always hard to find.
All right, so
But
just
in-
to
but in this
pause on
case-
this plot a little bit,
Yeah.
you've got the green dots, which are very small
Small pieces.
That's where they're physically located in this grid. So the overall grid looks like it's about 4 to 5 kilometers by a couple kilometers
Yeah.
in dimension.
So what was very unique about this case was that so the meteor came from the top,
Yeah.
from that direction, and
Mhm.
the winds were also blowing from that direction.
Yeah.
And what that does is it takes the small pieces and blows those on top of the big pieces.
Oh, okay.
And so instead of things being even spread out more, as you
Mhm.
sometimes have, and in this case everything was compacted.
It stays together. That's
And that's
interesting.
why when we went to this area here,
Mhm.
it took only a few minutes to actually
Yeah.
find meteorites. It's just,
Now,
just
what's the
amazing.
significance of those gray lines with the arrows? Is that your
That's
traverses?
what our search areas.
Really?
Yes.
Okay.
We did some vertical scans, basically lining a group of people, a lot of people from the village up and
Yeah.
doing these tracks and finding meteorites
Yeah,
in the
yeah.
process. And so that was quite.
So this is before you had the FDL drone and.
That was before they had
right.
the classical technique.
Yes.
yeah.
Yeah.
But
Fantastic.
this was a very lucky case in the sense that the winds were helping us. They were really, keeping everything compact. And from this, we also we learned how the rock was breaking apart. We also learned that the meteorite, when it came in the atmosphere, held together really well until about 27 kilometers. That last flare.
Mhm.
At that moment it broke and created this debris field on the ground. We haven't found meteorites that came from earlier flares. So
Okay.
we think that there were 4 flashes
Mhm.
before.
So
it
4
faded.
different breakup events.
4 different breakup events, but it looks like it's the final breakup event that it's when the rock fell apart.
So there could be. Oh, I see. But
Yeah.
so.
So there was
No other
smaller-
real debris.
No, less debris coming off early on.
Okay.
So what it says is that flashes are not always proportional to how much material you're
It's
creating.
breaking up. Okay.
Yeah, so it's an interesting there's an interesting complexity there.
Yeah.
Is how to interpret if you see a meteor in the sky, what does
What's
that mean
happening?
in terms of what's going on?
Yeah. So I want to get into composition for a second, but I see already that Rebecca's taking some questions down. So if you do have questions that you'd like to ask Peter, let us know, and we'll try and get to as many as you can. And again, you know, we always love to hear where you're watching from, so let us know. And you know, let's have some hearts and thumbs up for meteorites, meteorite hunters, detectives solving 22 million year old detective mysteries. And Peter, tell us a little bit about the composition, the analytical techniques,
Yes.
and also the significance of what the composition tells us.
Yes. So this is the detective story, and there's many puzzle pieces to it. It's difficult to say in what order to go from it, but maybe it's best to start here. So the first thing we did was we were able to determine that this rock came in on an orbit that was very short.
Mm-hmm.
It actually didn't quite, it just grazed the inner side of the asteroid belt.
Okay.
Coming in just towards orbit, and to have that short of an orbit basically means that the resonance which delivered it
Mhm.
was on the inner side of the asteroid belt. So this was the first evidence that our head meteorites, at least this one, came from the inner part of the asteroid belt. And that was sort of step number one.
Yeah.
Now it happens that Vesta is in the inner part of the asteroid belt, so
Mhm.
that was a good.
That's a good indication.
That's a good indication. So that's a good thing. The inclination of this rock was fairly high. It was about 23 degrees. Normally, if you find a rock fresh out of the asteroid belt, then the inclination is a sign of, the inclination, the angle in which the origin family is moving. But in this
Okay.
case, this steepness of inclination was probably caused by interactions with the Earth
Mhm.
or Mars, so the terrestrial planets.
Okay.
And so
the
we had
incline you're
already a
referring to
number of
is,
passages by the Earth before
Mhm.
it finally hit us in 2015.
And that angle you're talking about is the angle of attack ultimately when it comes in?
No, it's the angle that the orbit is at.
Okay.
So if all the planets move in one plane, the rock moves at an angle to that.
Right. But how are you
so
deriving
it goes
that?
around the sun like this, and you derive it from the way it impacts the Earth.
So you are deriving that from the
You get
angle
your-
of attack.
You get your trajectory, and then from that you get your orbit space.
Gotcha.
You have to take out what the Earth does to the orbit,
Sure.
because the Earth will curve the orbit in. And
Yes,
things like
okay,
that.
yep. All right,
So that was the first interesting clue.
okay.
The next step was that we found that this particular meteorite was actually from the very surface of Vesta, which is rare. So maybe 15 out of 300 somewhat meteorites of this type that are known, most finds, have this property. And so what it is this particular rock was found to have a lot of noble gas in it,
Mhm.
gas that comes from the sun,
Mm.
solar wind, basically.
Okay, so
that
it's
implants-
captured-
So it's really at the very
That's
surface
amazing.
of the asteroid. The solar wind penetrates these rocks, and
So you're
the
talking about
noble
like
gases
argon,
that
neon, et cetera?
in this case, neon.
Neon,
yes, yeah,
wow,
yeah.
okay.
And it also had a high admixture of iridium in it. And iridium is one of those elements that are fairly rare on Vesta, or generally in the meteorite, but that are being brought in by impacts from other types
From
of
others, okay.
asteroids.
So it's a result of the collision.
Yes, so it shows that you're really talking about the surface area there,
Mhm.
and that things things are impacting, meteorites are impacting, and ultimately that brings in this additional meteorite. So this rock came from the very surface layer of Vesta, and it was of a type that a lot of Vesta is covered in, this sort of Ukraite-rich howardite, and it's the howarites that show that, and so that's really an indication.
And what is that composition of the howardite?
That's really an indication that you're also dealing with Vesta. So
Yeah,
it's
yeah.
it's that surface of Vesta that has that howardite material, and then the very material that sits at the surface of Vesta. That's what we are seeing here as
Mhm.
a specific rock.
What's the chemical composition of that material?
So the the rock is different from other asteroids in the sense that you have what is called a basaltic meteorite material here. So it's an achondrite. It's not that primitive material that most asteroids are made out of.
Okay.
This asteroid is protoplanet. We're talking Vesta.
Mhm.
At some point in its history, differentiated. That is, iron-loving materials
Yeah.
sank to the core,
Mhm.
and whatever was left over came to the crust.
Interesting.
And just like the Earth did, we have an iron core on our planet,
Yeah.
and the material we are sitting on is poor in iron.
Yeah.
And that's the case with Vesta as well. Now, there are very few asteroids known that have this property, so that makes Vesta sort of unique.
And so when you find that material in
And
the
that is
meteorite, it's a
a
good
reason
indication.
why people for a long time have said, well, it has to be this link
Yeah.
to this type of meteorites in Vesta.
Yeah.
But there are other meteorites, and as a matter of fact, the one other type of this type of meteorite that was photographed coming in
Mhm.
was Bunbury Rocco in Australia a couple years earlier, and that meteorite turned out to belong to the other,
The other.
not the Vesta,
Category,
but the
yeah.
other category.
Yeah.
It had isotopic signatures that were very different.
Mhm.
And so we were pleased to find that this meteorite actually had the isotopic signatures that were common, that were, 1/3 of all HED chondrites coming in have
Have
these
that
properties.
composition.
This belongs to just a most common type of a HED falling to the Earth.
Mhm.
And that means that this rock came from a really big collision event.
Yeah.
We're talking an impact or a disruption of an asteroid that generated enough material to now be responsible for 1/3 of all the rocks.
it-
And that collision happened 22 million years ago.
And is it possible to estimate the size of the other object that impacted Vesta in that collision?
If you can identify the crater.
Yeah.
So the
Okay, so you
next-
don't know which crater.
You don't know, yes.
necessarily.
So that was the next step. The evidence we had was that this came from a significant impact event. It looks like it came from the surface of Vesta, being a regulated howardite. It had a 22 million year, what we call cosmic ray exposure age. That means that as a rock, about a meter in size, so the rock when it hit the Earth was about this big.
Mhm.
As a rock this size, it had been in space for about 22 million years.
Amazing.
Yeah.
Amazing.
And doing its, going around the sun
Spinning.
all that time.
Yeah. Yeah. Wow.
And that meant that we were looking for a crater that was 22 million years old.
Mhm.
And so the next step, of course, is to go and look at Vesta, look at all the mapping of the craters that
Right,
were done,
right.
and to see if you can find a crater that's 22 million years old.
And how do you age the craters through
And-
image analysis?
And you need to find a big crater that's 22 million years
Yeah.
old.
Yeah.
And so, so the way craters are dated is really interesting because a lot of controversy there too. The craters that you can date are the ones that still have this ejecta blanket around it.
Right.
And I have a picture here of.
Oh, that's good.
Yeah, this is actually the crater we identified as the one where we think our meteorite came
So
from.
pretty much,
Antonia.
if you're looking on your Facebook page, it's pretty much that crater in the middle of the image.
Yes,
Yeah.
exactly.
Okay.
And this is a color composite made of different images, so it brings out the mineralogy of the terrain.
Mm.
And what is green colored is basically material that is freshly exposed to the
Oh,
surface.
so that's the ejecta from.
That's ejecta blanket. And you
Okay.
can see that some craters have this and most craters do not. I mean, none of these craters have this ejecta blanket, but this one has it there, and this one very clearly has.
Yeah,
You can
that's
see there's a
amazing.
lot of green here with a big fan going all the way south.
Yeah,
This
yeah.
one has it as well. And so these are the craters that you can try and date. And what
Mhm.
you do is you look at this terrain and you count the number of small craters on it.
On top of the bigger
On
crater.
top of this ejecta.
Ah, okay.
So the impact happened. You're spreading all this debris around.
Mhm.
So now you're creating a new clean
Fresh
surface,
field,
fresh
yeah,
surface, and now you're going to pummel it with small impacts over time.
Yeah.
And the longer you wait, the more
More.
impacts you're going to.
Okay.
And so.
So it's an averaging technique.
It's
I
averaging
guess. Yeah.
technique.
Yeah.
And so what makes it controversial is that we really don't know how many small impacts happen every year.
Yeah. Right.
And so you have to make some assumptions about, how many of these small impacts happen.
And whether that's uniform
whether
or
it's uniform,
not.
how is it distributed, and so on.
Right,
And
right.
so what are the impact speeds? And there are principally two models out there that people use to get these ages. And one is based on theoretical modeling, where they look at the asteroid population, they put a lot of dynamics in it, a lot of what happens to meteorites when they're in space, they get moved and disappear and so on. From that you get a size distribution, velocity distribution, and from that you can determine how much stuff is hitting the asteroids. That asteroid model, impact, that sort of asteroid-based chronology, makes all these craters too old. So it basically would say that all of these craters you see here as fresh craters that happened recently, they are all way too old to have created the stuff that we are seeing.
I see. Okay.
And so that doesn't work for us. If it turns out to be the correct chronology age, then we're wrong. Then the story isn't right. But the other chronology age, which is basically to look at the moon, the lunar surfaces, which we've been dated by the Apollo landers,
Sure.
and to look at those surfaces and look at the impacts on those surfaces, and from that get a distribution.
See if you can make a correlation.
And then make a correlation, and if you do that, then you get what is called the lunar-based chronology scheme. And in the
Okay.
lunar-based chronology scheme, this crater is 22 million years old.
Interesting. Now, in the other chronology base, how old is it? thought to be?
I forgot the number, but it's like 4 times or so, 2 or 4 times older.
Older.
Yeah.
Wow. So it could be
Everything is
100
old.
million years old.
Yes.
Wow.
And that would make it way past any of our meteorites. Most of the meteorites we're
Uh-huh.
getting are less than 100 million years old.
Okay. Okay.
So, we looked at other craters on Vesta.
Yeah.
And we looked at other meteorites that have different cosmic ray exposure ages. And if you look at the distribution of those crater ages, you too find that you can build up a case to say that this is actually the correct age, because a big crater that is somewhat older looks to be responsible for a peak that we have around 50 million years.
Yeah.
And some craters that are younger look to be responsible for some HEDs that are younger.
A different one.
And
Different
so,
set.
so that's another piece of the puzzle. There you say, okay, with that chronology age, you're consistent with what we are getting
Right.
to come to Earth.
Yeah.
And that makes that particular crater, a significant crater, 16.7 kilometers in diameter. That makes that our source of this meteorite.
Excellent.
And then, of course, other steps in the puzzle are that you cannot play this straight just on the ejecta blanket. You can also look in the area around it,
Sure.
and you can get a sense on how old is this terrain. And turns out that terrain is, about I think 1.4 billion years or so. It's a lot older.
Billion years.
Yeah. We're
Yeah.
talking now much further back in time.
Mhm.
And the reason it has that age is because, as you can see, Vesta get constantly pummeled by stuff, and so all that debris from these craters lands up on the surface of the dwarf planet, and so it builds up this layer of material that, on average, has sort of that 1.4 billion years.
Yeah.
It turns out that our meteorite also seems to have experienced this sort of impacts, in a sense that it has lost some of its helium. And we are
So
thinking.
in other words, even after it was
we are thinking
ejected,
that
it had its own impact.
yes, it experienced its own nearby impacts that
Yeah.
heated it at the pressure,
Yeah.
and that made some of the helium go away.
So you're not finding as much helium as you would expect.
As you would
in other words.
expect.
Interesting.
Exactly. And that age too is consistent with the terrain age.
Okay, so that's what you're saying when
Yeah.
you've got a lot of evidence from different perspectives, all pointing to the same
All
answer.
little puzzle pieces.
Yeah.
Yeah. And then, of course, you have the study on dynamics, which Mikko Granvik did in Finland, where you look at how long does it take to get from Vesta to come to one of these resonances,
Mhm.
and then go from the resonance, have these interactions with the Earth, and ultimately hit the Earth.
Yeah.
And we found that the first step is very quickly,
Mhm.
so getting from a collision on Vesta and then dispersing this stuff to the resonances, that happens within 1 million years,
Mhm.
2 million years. But then once it gets into the shorter orbits where radiation doesn't matter so much anymore, where it's really the interaction with the planets that makes the change,
Yep.
it turns out that that time scale is also consistent with it, sort of arriving right at the peak of the arrival time. So
Mhm.
basically, at this moment, we are seeing the stuff from Antonia come to the Earth.
Mhm.
The younger craters, the craters that happened more recently, they put out a lot of material, but that material is still on its way.
Yeah. Yeah.
And the bigger craters that are older, they have long, all the material has long been lost.
Yeah. Yeah.
And so Antonia sits right at this time that sort of is at this peak that you would expect stuff to come from Vesta. And then, of course, that settles arguments on okay, so how much material do you need?
Mhm. Mhm.
If you're not right at this peak, then you need a lot more material, you need a lot bigger crater. But it turns out that Antonia is big enough to have generated enough pieces
Yeah.
for there to be the rate of impacts that we're now seeing at the Earth. So it's a long detective story. There's
Yeah.
many pieces to it.
And you had quite an international team, right? You had
Yes.
how many different countries are represented on this team? It seems like
a lot.
a couple of dozen or
A
more.
lot,
Yeah, yeah. Well, let's first of all, we'll do a little shout out to all the parts of our own planet where people are watching from, and then go to some questions that have come in. So we have people from Port Orchard in Washington, from Kristiansand in Norway. This must be the same person because we're always getting someone from Kristiansand. So great to have fans in Norway. From Saskatchewan in Canada, Burbank in California, Charleston, South Carolina, Christchurch, New Zealand, Berlin in Germany, Kassel in Germany, from Italy, from Scotland, from the UK, from Barcelona, from Edinburgh, from Oaxaca in Mexico, from Pennsylvania, from the Jersey Shore, or the Jersey Shore, Jersey Shore, we would say, Palm Springs, California, Texas, or Texas, Pasadena, California, Joinville, Brazil, if I'm saying that right, Mountain View, right here, Connecticut, Arkansas, Columbia, Maryland, Melbourne, Australia, Lisbon in Portugal, Milan in Italy, Genoa in Italy, Sintra in Portugal, I've been there, Tasmania, Cape Breton in Nova Scotia, Cedartown, Georgia, Phoenix, Arizona, Kent, UK, Kurdistan, Istanbul, there we go, Tokyo in Japan, Izmir in Turkey, another visitor from Turkey, from Izmir. So welcome everybody, and thanks for joining us. It's again, it's to me a sign of how science unites us as a people on one planet by having curious people from all over the world joining us on these. So a question comes in from Brandon, which is, what is the scale? So if you, I had that same question. If you go to back to that first picture, the pink background one, what was the scale? How big is that meteorite piece in that first photo?
That meteorite piece in the first photo is this one that I showed.
It's the one you showed us.
Yes,
So
yes, it's just very small.
a little less than 2 centimeters or
Yes.
thereabouts.
Yeah.
Yeah. Okay. Okay. And then how does the material affect how it will look? So I think that may refer to how does the composition affect how it will look? Because
Yes.
there's also what happens as it heats through the Earth's atmosphere that affects how it
Yeah.
looks. What can you say about?
So the blackness of the crust of a meteorite is caused by iron.
Mm-hmm. Okay.
And so it does depend on how much iron there is in your rock and how dark it's going to look.
It's funny, I would have thought carbon, but it's iron.
No, it's the iron
Interesting.
in the glass. And
Mhm.
so in that sense, composition does affect the look of it. And certainly, if you have a metal meteorite, it will look very different.
Yeah.
You know, but as a sort of rule of thumb, most meteorites that are falling to the earth will have a really black crust.
Mhm.
The inside can be light, it can
Mhm.
be very dark,
Mhm.
but the outside will have this black crust.
And that's really the burning.
And that's really from the melting. It's
Yeah.
really this melt layer, and then the fact that you create iron that rusts, and And one of the things that the Bulgarian team found that you make magnetite crystals.
Mhm. So that question came from the International Science Fiction Society. So
yeah.
we may find something about this in a future science fiction novel coming.
I've seen meteorites that were made of pyroxene that had very little metallic iron in it and so on, and they turned out to have a green crust.
Okay.
So so the composition does
reveal itself.
Does reveal itself
Yeah.
in how it looks, but yeah.
Stephen asked, what is its mineral composition? So we've talked a little bit about that. Anything more to say about its makeup? Is it?
No, it's.
Is the largest percentage of material iron? Is that, if you break it down in terms of the percentage
Yeah,
distribution?
I think that it's fair to say that basaltic materials, which is unlike organoids, but this type of basaltic materials is really in composition somewhat similar to if you go to Hawaii and you look at lava
rocks
sometimes there. But in detail, of course, that's not the case because the depth from which material comes and the evolution has been different.
Yeah.
But there's been this same sort of process where you differentiate the mantle from the core.
Another question was, how do you estimate the winds? Maybe that's a reference to how the wind affected that debris field.
Yes.
I mean, I guess you've got wind speed from the meteorological services, I suppose.
Yeah, exactly. No, you need that. That's important. We get our wind data usually from windsong measurements.
Okay.
They're all public on a global scale, and you can find sites not too far from where you live that has a vertical wind profile measured by meteorologists who ladder balloons. And so from the ground until about 20 kilometers is where you get your wind field that way.
Okay.
And it's and that's usually precise enough for what we need. If you want to more precise or want to look at higher elevations, then you can go to atmospheric wind models, and then you can specify where you are, and then you can take your data from that model. And the models are really good these days as well.
Yeah.
So you will find small discrepancies, and that's part of the interesting thing to come out. Yeah.
Cool. Okay. Let's see. What is the largest meteorite you found, and where did you find it? Don wants to know.
I don't think size matters. It's more. I mean, it's more about what is the most interesting meteorite.
So why don't you answer both? Because some people think, big ones are cool because they
the thing
make
is,
more noise, but
yeah, the thing is that with
and what's the most interesting?
The type of studies we do, usually a small meteorite is gives a lot of information. You can get a lot of data out of a small meteorite. So if a meteorite is found and a small piece can be made available to science, then we can do a lot with it and really learn a lot about this meteorite. Interesting meteorites at this point in time is almost everything, because even for the meteorites that are very common, what we call the ordinary chondrites, we call those ordinary because that's what you usually get if you actually have a meteorite. It's an ordinary chondrite. Even ordinary chondrites, we have very few for which we actually have the approach trajectory measured. And from the three types of ordinary chondrites that are most common, the L, LLs, and H's, for each we have maybe 5.
Yeah.
And those 5 tend to be from 5 different collision events. And so for us to get statistics on, where, from what direction, what orbits do our meteorites fall to the Earth, we really want to have lots of meteorites. So if we had a lot more meteorites from this particular type, then, for example, we should be able to see this phenomenon where the rock interacts with the Earth. So we should have a tail of inclinations. We have low inclinations and going to higher inclinations. So I don't so much care for size. I care for.
So then answer it in terms of interest. Where is there one that you consider the most interesting one you've ever found?
Yeah. So my interest, I have an interest in the meteorite. The moment we have video data or radar data or any type of data that shows the impact trajectory.
Okay.
Yeah.
So it's that combination of knowledge of having the physical meteorite itself, but also knowing
from what direction it's
from
coming.
what direction it comes.
Because that is ultimately going to help us with this detective story on which debris fields in asteroid belt is giving us our meteorites.
And is this an example of one where you had like the best kind of trajectory information because you had so many different views on it?
No. This
What's-
was a case where we made do with what was serendipitously obtained with security cameras.
Yeah.
But so video security cameras are not cameras designed for doing this work. So you have to put a lot of effort in calibrating the data. But we did, and in the end, the result we got, I think, was good enough for what we wanted. It gave us an inclination, gave us the image axis, precise enough to tell the story.
Great. All right, we just got a couple minutes left, so let's get to the last couple of questions. Do meteors get tested for signs of life, like bacteria that may have survived inside the meteor? Don, again, is asking that question. Good
Yeah.
question.
As
You ever look for organics or?
we're looking for organics, we're very interested in organics.
Sure.
And so in a way the answer is yes.
Mhm.
The way we do it, though, is you don't look for DNA, you look for the basic organic compounds
Yeah.
that are typically in meteorites, also from other sources.
Mhm.
And what we did for SETI check is we specifically looked at amino acids. If you
Okay.
have life, then you would expect to see that.
Mhm.
But life has a way of selecting one type, the L, versus the D type amino acids. And so from the relative ratio of the two, you can actually tell whether you deal with life, or as we call it, contamination,
Uh-huh.
or whether you deal with the intrinsic material that was
Right,
there from
right.
when the meteorite was made.
Mhm.
And so we do that. We also look at methanol soluble material. So the amino acid work is done at NASA Goddard.
Mhm.
Uh,
NASA
the,
Goddard, okay.
Yeah, the organic work on methanol soluble compounds is done in Germany,
Mhm.
the Helmholtz Institute, and there they do ultra high mass spectroscopy. So they look at things that are soluble, but then they look in incredible detail at what compounds there are, and they can see these different groups. They can see organic compounds also from things that interact with the minerals.
Yeah.
So they see magnesium compounds, so it's very interesting. So we do
Fantastic.
that, and then we also look at PAS,
Mhm.
stuff in cigarettes,
Yeah,
also
yeah.
contamination sign, but also very a sturdy type of molecule that you find many places.
Mhm.
And these organic compounds tell also a story on what happened to this rock
Yeah.
over time. And usually in this case, the organics was very little. We expected to find more from just the carbonaceous chondrites hitting the rocks. In this case, there was very little. But we did find some that was intrinsic.
Excellent. Okay, here's an interesting question. Are there materials in space that are outside our periodic table? So far not.
No, not to our knowledge.
Not
of
to our
course,
knowledge,
because otherwise it would be in the periodic table.
Right.
But there are materials in space that you typically do not find on the Earth because
Right.
of the environment
Yeah.
that we have, the temperature, pressure, water being here. And we are interested in those compounds.
Well,
mean,
it
you
relates
can-
to the story
relates to the story.
of the
Yeah.
demise of the dinosaurs, right? It was
Yes.
finding a layer all over the planet of material that was really unique to
Yes.
asteroids that suggested it was asteroid impact, a massive one that
Just
did in the
remember
dinosaurs.
that space is nothing like Earth.
Mhm.
It's vacuum.
Yeah.
It's radiation. It's heat. It's just conditions that are extreme for
Yeah.
us,
Yeah.
and that means that if you bring a piece back and you can keep it in pristine, in good shape,
Yeah.
you can find things that are really interesting. And so we very much like a meteorite. When somebody finds a meteorite in the backyard, please
Don't touch it.
don't touch it.
Yeah.
Use a piece of aluminum foil to pick it up.
Yeah.
Keep it clean. Keep it away from
Call Peter.
Yeah.
And
call
if
us.
you're lucky, you'll get a post-it that he will save for years about the call that you made that said, "Hey, I've got a meteorite in my backyard." A question from our own audience, Rebecca.
How do you know if it's a meteorite and not just a regular old rock?
So you look for the fusion crust. That's really the thing.
Okay, but
Yeah.
what if you're just a regular person and you've never heard of a fusion crust?
You go on the internet and you Google fusion crust.
Well, no, I
Because-
mean, I think
Because that's really the one thing that usually tells you that you have a meteorite. It doesn't always work,
But that glassy black
Yeah.
surface.
Yes, exactly.
But yeah, if you find something and you're curious about it, as Peter says, don't touch it. Pick it up with aluminum. You could probably take a good high resolution picture with your
Yes.
camera phone. Email it to us if you do think you've got something interesting. Follow those steps, and we can perhaps help. I guess they're common enough. They happen all over the world, so
Yes.
you can find them.
To the level that a meteorite could be sitting in your backyard, literally.
Yes. Yeah.
Meteorite falls happen quite frequently. They're very rarely found. So we only have about between 8 and 12 or so times per year that somebody reports having a new fall. So
Yeah.
this one in Turkey was very exciting because here was a case.
Well, and these meteorites tell us a lot about the formation of our solar system, about the composition of materials that are left behind from the creation of our solar system, and about the formation of the planets, and about maybe how origins of life stories. So they're very important and exciting and interesting, which is why Peter here has been spending his entire career looking for them, studying them, analyzing them, and has traveled the world and actually put his life in peril, apparently, in pursuit of them. So, Peter, it was great talking to you about this. If you want to learn more about this event, again, you can go to our website and find the press release that was issued on March 18th called Turkish Meteorite Traced to Impact Crater on Asteroid Vesta, a 22-year-old collision mystery. And with that, we want to thank you for joining us again from all over our planet, and for spending some time with us here in Mountain View at the SETI Institute. Peter, thanks as always for helping us again and for sharing this great story and this exciting news. And thank you for your colleagues and for Ozan for joining us from
Yes.
Turkey. That was great to know that he was watching us. All right, so from Mountain View, California at the SETI Institute, Bill Diamond and Peter Jenniskens and our crew saying goodbye, and we'll see you next week. Thanks, everybody.